Hi everyone, and welcome back to another project by the Gapplebys. Today, Karloot, James, and I will be talking about phase diagrams.
What are phase diagrams? A phase diagram is a graphical representation that shows the relationships between temperature, composition, and sometimes pressure for different phases of a material or a mixture of substances. It is a critical tool in materials science, chemistry, and engineering as it helps to understand the conditions under which specific phases of a substance are stable.
Here we have the phase diagram of our alloy, titanium aluminide. We can see that there are many different kinds of cooling reactions, so let's dive into a few.
How are crystals formed through different cooling reactions?
The first cooling reaction we're going to talk about today is an allotropic reaction. An allotropic reaction is a change in crystal structure without changing chemical composition. We can see that with pure titanium on the left side where there is a 0% composition of aluminum marked on our phase diagram with the purple dotted line. Starting from the liquid phase and cooling from there, we start with our top purple circle. This circle is liquid titanium. At a temperature of about 1950 degrees Kelvin, or about 1678 degrees Celsius, our liquid titanium becomes solid beta type titanium. This beta-type titanium is more stable at higher temperatures and has a body-centered cubic structure. As we keep cooling, we approach a temperature of about 1150 degrees Kelvin or about 877 degrees Celsius. At this point, our pure titanium becomes alpha-type titanium, changing crystal structures to hexagonal close-packed. We see that along this line, titanium does not change chemical composition, but does change crystal structure, making it an allotropic reaction.
In this second cooling reaction, this discussion focuses on the peritectic reaction in the titanium-aluminum alloy system and the application of the lever rule to determine phase proportions around 1750 Kelvin. At approximately 1750 Kelvin, the alloy enters into a two-phase region where both solid and liquid phases coexist. The light blue line and the dark blue line represents the boundaries of these regions, with the purple vertical line indicating marks of the alloy composition at this temperature. The red line indicates the tie line at this temperature. The peritectic reaction occurs when a liquid phase and a solid phase transform into a new solid phase. This process is highlighted by the transition through the specified phase boundaries at 1750 Kelvin, where the tie line connects the coexisting liquid and solid compositions. Using the lever rule, the proportions of the solid and the liquid phases can be quantified in these two phase regions. For the light blue section on the left, calculations show that the fraction of solid is approximately 42%, while the fraction of liquid is about 57.1%. This indicates a dominance of the liquid phase at this temperature. Similarly, for the dark blue region, which corresponds to a different tie line on the phase diagram, the fraction of solid is around 20%, while the fraction of liquid increases to 80%. This further demonstrates that the liquid is the major phase under these specific conditions.
In a eutectoid reaction, one solid collides with other substances and turns into two other solids. In this case, at about 1350 Kelvin, our solid titanium collides with 55% weighted aluminum to partially turn into TiAl2 and partially into TiAl. Both of these resulting compounds turn out to be two more solids, making the reaction eutectoid. During these changes, the structure of our original titanium portion changes from hexagonal closely packed to two differing forms of tetragonal structures. To use the level rule, we take the value of x sub s and subtract the total length of the line. We then divide that all by x sub s minus x sub l, getting us the mass of the liquid. To find the mass of solids, we change the numerator to the total length minus x sub l. Doing this, we find that m sub l is 50% and m sub s equals the other 50%.